This video contains solutions for the step-by-step problems that are missing in other videos for Chapter 8. Numbers 8, 13, and 14. So number 8, we have function f of x is equal to 12x over x squared plus 6x plus 8, and we know that g of x is equal to 1. They gave us a little graph, and we can see that those two functions intersect at 2 and 4, and you could check that if you want to. And they want us to show that Rolle's theorem holds for f of x on the interval from 2 to 4. Rolle's theorem is a special case of the mean value theorem that says if you have 2 points that have the same y value, and that on a function that's continuous, that there must be a place in between where the derivative is 0. Of course, that's just the mean value theorem here, because the average slope would be 0. So what this is asking us to do, show that Rolle's theorem holds, we would have to find f prime of x, set it equal to 0, and show that there's a solution in the interval 2 to 4. Right? That's what that would entail. So let's do that. So the derivative of f, using the quotient rule, low d high minus high d low over low low. I'm not really going to have to do anything with the bottom here because I'm only interested in it being equal to 0, so that'll be when the numerator is equal to 0. So let's see. I get a factor. I've got a 12 here. I can go ahead and factor that out. I'm going to do that. It gives me x squared plus 6x plus 8. Then my 12 is gone minus 2x squared minus 6. Right? 6x, sorry. And that's what I'm interested in, being equal to 0. So the 12 doesn't matter. That's not going to be equal to 0. So x squared minus 2x squared, 6x minus 6x is 0, 8. So it looks like my solutions are x is equal to plus or minus the square root of 8, which is plus or minus 2 square roots of 2. Now the solution I'm looking for, I'm not interested in the negative one. I'm interested in this one, because that's in the interval from 2 to 4. Right? So we have shown that Rolle's theorem holds by showing that there's a place where the derivative is equal to 0 and the interval shown or given. Part B, we're going to find the area of the region R. So the area between two curves is the integral of top minus bottom. They intersect at 2 and 4. Excuse me. So top is 12x over x squared plus 6x plus 8 minus the bottom one is just 1. And to do this, it's like we have to do partial fractions here. So let's see, if I factor that, that factors into x plus 2 and x plus 4. So my a and my b. So that would be ax plus 4a plus bx plus 2b all over my common denominator. So I don't have any, oh, I do have extra, sorry, and I forgot an x there, didn't I? So a plus b, the coefficients of the x's, would have to equal 12. And the constant terms, 4a plus 2b, would have to be equal to 0. So let's see, how about if I multiply this equation through by negative 2? It would be negative 2a minus 2b equals negative 24, and that gives me 2a equals negative 24, So a equals negative 12, and b is equal to 0. That doesn't work. What did I do there? Let's see. Multiplied that equation by negative 2. Oh, sorry, b wouldn't be 0. b would be 24, wouldn't it? There we go. And I check that in this equation, and yeah, that works. Okay, that's better. So my integral now turns into the integral from 2 to 4. The coefficient here, a, is negative 12, so that would be negative 12 times 1 over x plus 2 plus 24 times 1 over x plus 4 minus 1. Finding antiderivatives, that's minus 12 times the natural log of x plus 2 plus 24 times the natural log of x plus 4 minus x from 2 to 4. And that gives me minus 12 times the natural log of 6 plus 24 natural log 8 minus 4 minus, plugging 2 in, minus 12 natural log 4 plus 24 natural log 6 minus 2. And if you do a little simplifying, I'll leave this to you to try to simplify it. If you got this far, that's super. You can get that to simplify by making this 2 to the 3rd power and bringing the 3 to the outside, making this 2 squared and bringing the 2 to the outside. Then all the terms are either natural log 6 or natural log 2, and you can combine stuff and get 96 natural log 2 minus 36 natural log 6 minus 2. You can get it to simplify to that. All right, part C of that problem. Region R is the base of a solid. For this solid, the cross sections perpendicular to the x-axis are, here's my region R, are semicircles. And they want us to write the integral for that. So here's each one of the cross-section bases here. If you pull one of those out, there's my semicircle. So this right here, that's the distance between the top and the bottom function. So that would be f of x minus g of x. Right? Right?
Right.
So that is the diameter of the circle. So the radius of the circle would be half that, f of x minus g of x over 2. And the area of a semicircle is 1/2 pi r squared. So to find the volume we're interested in, we need to do the integral from 2 to 4 of this area formula of semicircles. So the 1/2 pi can go outside as a constant. And then here's my r, f of x minus g of x over 2 squared. So that's the integral. And since they defined f of x and g of x up top, I can just write them as f of x and g of x. You don't have to write in the functions if you don't feel like it. All right, that's number 8. Number 13. Let's see. We want to find, first of all, the absolute maximum value of g on the interval from 0 to pi, if it exists, and then justify our answer. Okay, so here's the g of x function. If I want to find the maximum of it, look for places where the derivative is equal to 0. So the derivative of that would be low d high, that's just 1, minus high d low over low low. Interested in where that is equal to 0. So that's where the top's equal to 0. So let's see what we have here. I've got x squared plus x minus 2x squared minus 2x minus x minus 1 equals 0. Simplifying that, x squared minus, that's minus x squared plus x plus 1 equals 0. So x squared minus 2x minus 1 equals 0. That doesn't factor. So let's see. If I use the quadratic formula, you could actually complete the square here if you wanted to. It'd be pretty easy to do in this problem. Well, you can use the quadratic formula, whatever you want. So opposite of b plus or minus the square root of b squared minus 4ac all over 2. And that all turns into 1 plus or minus the square root of 2. And since I'm looking from 0 to infinity, we have a critical point at x equals 1 plus the square root of 2. 1 minus the square root of 2 is negative, and that's not part of our domain, so not interested in that. If I make a sign chart, this thing here, the top of this, was a downward opening parabola. That's one way of looking at it. So that would go from minus plus minus. The minus part is out of our domain. The plus would be the part from 0 to 1 plus the square root of 2. And then it would be minus after that. So it goes from positive to negative, and those are the only critical points. So that is, in fact, the absolute maximum value because it's the only maximum. So I could say, for my justification, there's a max at x equals 1 plus the square root of 2 because the derivative, this is the g function, isn't it? G prime of x goes from positive to negative. Find the area of the unbounded region between f and g to the right of the vertical line x equals 1. So the region between f and g, that's the integral 1 to infinity. Which one's on top? F's on top, so f of x minus g of x dx. Now I'm going to take a minute and just find an expression. There's more than one way to do this, but I'm going to go ahead and find a common denominator here for this expression. So I have 1 over x minus 1 over x squared plus x is x times x plus 1. So this is missing the x plus 1 top and the bottom. So that's equal to x plus 1 over the common denominator minus x minus 1. That already had the common denominator. And if I simplify that, the x's cancel and I get 1 plus 1, 2 over x times x plus 1. So that's a simplified version of that. To find the antiderivative of that, I can do my partial fraction decomposition. I've got my two factors, a over x, b over x plus 1. That's ax plus a plus bx all over the common denominator. So a, the constant term, would have to be equal to 2, and a plus b would have to be equal to 0 because there's no x term. So if a is 2 and a plus b is 0, that means b would have to be negative 2. So, got the integral from 1 to infinity. Now I have a is 2 times 1 over x, minus 2 times 1 over x plus 1. And that's equal to, I'm going to go ahead and factor the 2 all the way out to the front. Antiderivative here, that's natural log x minus natural log x plus 1 from 1 to infinity. Now, the next thing that you really should do here, if you go ahead and try to plug the infinity in, you get natural log of infinity minus natural log of infinity, which is really an indeterminate form, because you don't know which one of those infinities is bigger or racing off to infinity faster. So what we should do here is use logarithm rules to consolidate this into one logarithm. It would be natural log x over x plus 1, right? Because subtraction turns into division like this with logarithms. And now, when x goes off to infinity, this turns into 1 natural log of 1 is 0 minus, and when you plug 1 in here, you get the natural log of 1 over, oops, sorry, that's a plus there, 1/2, and negative natural log 1/2, that negative could come in here and flip that, so that's equivalent to 2 natural log 2. Right? Part C. The unbounded region between f and g to the right of the vertical line x equals 1 is the base of a solid. For this solid, the cross sections perpendicular to x are squares. They want me to write, but do not evaluate an integral that represents the volume of this solid. So same thing, 0 to infinity. Now the distance between these is just the side of a square. The distance between them would be f of x minus g of x. So that distance squared. That's it. Now whether that's defined or not, we don't know. All right. Number 14. This is an interesting problem, general sort of problem. Maybe a little bit confusing to crack exactly what's going on here. So first of all, they want us to show that the limit as b approaches infinity of the integral from 1 to b. So that's the same as saying, I'll just write it on the graph here, saying the limit as b approaches infinity, the integral 1 to b, that's the same as this improper integral. There is no difference at all between those two things. B is going to infinity, so just go ahead and write the infinity there. Right? If you run into somebody who objects to the fact that you're writing infinity as one of these limits of integration here, you could say, oh, well, this is what I mean. I mean, if there's a limit as b approaches infinity of this, then we'll call that this. So that's really what we're doing. So first thing, I think maybe we just want to think of it as this. So let's just write it down as that and think about that for a minute. So the integral from 1 to infinity, 1 over x to the p dx. Well, we've done some problems like this in section 8.8, and we talked about, or I talked to some people about at least, that we might have a sense now of when these things are going to converge and when they don't converge. So that's the idea that we're playing around with here. And we know that if this is just 1 over x, then the antiderivative of that is natural log x, and when you plug the infinity in, you're going to get natural log of infinity, and that is going to go off to infinity. So that would be an integral that would diverge. But if this was 1 over x squared, then the antiderivative of that, the x will still be in the bottom, and then the infinity is on the bottom, you get a 0 there, and then you get an actual value for the area. So there's something going on, and that's what this question is about. It's about that boundary and what these maybe generally are equal to. All right, so let's do it and see if we can make sense of all that. 1 over x to the p is the same as x to the negative p. What's the antiderivative of x to the negative p? Well, to find the antiderivative using the reverse power rule, we add 1 to the exponent and divide by the new exponent. Right? Now I'm going to have to plug infinity into this. And like we were just talking about, if you want this x to the infinity, infinity to this power, if you want that to be equal to 0, we need for this to be defined for the infinity to end up on the bottom. And if the infinity is going to end up on the bottom, that means that this negative p plus 1 has to actually be a negative exponent, right? If this is a negative exponent, then the infinity will end up on the bottom. So I need, this is okay if the exponent, negative p plus 1, is negative. That's what's going to make that work. And moving that p over here, that happens when p is greater than 1. So first of all, p has to be greater than 1. If p is greater than 1, then when I evaluate this integral, I get infinity to the negative p plus 1 over negative p plus 1 minus, when I plug 1 in, I get 1 to any power is just 1, over negative p plus 1. Now, if p is greater than 1, then this will end up on the bottom, and this term will turn out to be 0. And I'll get negative this. The negative sign could just swap the signs of those. So that would be equal to 1 over p minus 1. And we have actually done what they asked us to show. They asked us to show that this converges to 1 over p minus 1, but it only does so if p is greater than 1. So that's an interesting problem to think about. And it reinforces that thing that we were talking about, that the natural log function is kind of a boundary function, above which things diverge and below which things converge. This part, totally new problem here. I've got the figure at the right shows the graph of y equals x e to the x minus this. Note that the graph is discontinuous, and they want to find the area of the shaded region. So the first thing that I want to convince you of is that, when we do this integration here, and we're integrating a difference like this, you could separate it into two integrals like this, right? When we evaluate them, we're effectively doing it piece by piece anyway. So that's the same as that. And then I just want to convince you first that this is equal to 0. So when you have the absolute value of something over itself, that's either equal to 1 or it's equal to negative 1 in the case where this is negative and that's the positive version of it. And this one switches, the absolute value signs switch from being on to off at 1. So this right here, just that piece, you might remember things like this from our limit chapter way back when. So the area from 0 to 2 of this, well, you got negative 1 area and positive 1. It's just 0. So this whole piece of this is 0. So the whole shifting a little bit up, down, it didn't make any difference at all. It's all a wash in the end. So really what we need to do is just evaluate this. And to find the antiderivative of this, that's a tic-tac-toe integration by parts So I have x, e to the x, x, 1, 0. Antiderivatives of e to the x are e to the x. That's plus, that's minus. So the antiderivative is x, e to the x, minus e to the x from 0 to 2. So that's when I plug the 2 in, 2e squared minus e squared minus, that would be 0, minus e to the 0. Be careful with signs here. So 2e squared minus e squared, that's just 1e squared. And then minus 1 is plus 1. So e squared plus 1, which happens to be my lucky number.